Okay, so as the title suggests, we're going to be looking at the trapezium rule, and the trapezium rule, I hope you're familiar with it from GCSE maths, where it's introduced in a slightly informal way, where you might just calculate the area of 3 trapeziums to approximate the area under a curve. Here, we're going to actually give the formula, and again, just go over the logic behind the trapezium rule. So, if we have some xy plane, okay, and then we have some graph marked out by y is equal to f of x, and we want to find the area between the points x0 and xn under the graph. The technique of the trapezium rule is to split this into, as the name suggests, trapeziums of equal width. Okay, and this width is denoted h. This point we call x1, we call this x2, x3, x4. Point is, we could have more x's, so we're working from x0, x2 all the way up to xn minus 1 plus xn. These points here, these are our y-ends. Okay, so y-ends equal to f of xn. It's the value of the function at the value xn. And what we're doing is we're calculating the area of all these trapeziums by connecting up the points. And you can see, like here, we get a slight overestimate. We get a bit of over here, a bit of under here. Sorry, this is an underestimate and stuff. So these approximate under and overestimates should hopefully cancel each other out to give us a reasonable approximation of the area of the curve. Obviously, the more strips you have, so the smaller you make h. So if we were to draw the same graph, well, try anyway. If we were to try again this technique, and we made the width of the windows even smaller, and therefore, as a consequence of that, we'd have more of them. You can see when we draw these straight lines, the straight lines much more closely approximate the graph in that region, so we get a better approximation. The formula is given by, so we're going to denote the area as the integral from xn to x0 from f of x to dx, because that gives us the area. You might think, well, why don't we just integrate them? Well, the whole point of this is when sometimes we have a function that is certainly difficult to integrate, if not impossible, or an approximation is fine. We don't need the exact area. Okay, so this is equal to, I should say approximately equal to, terrible handwriting, let's draw that again. That's a little bit better. Is equal to 1/2 h y0 plus yn plus 2 y1 plus y2, keep going up to yn minus 1. And we might want to think about why this is true. So if we're looking at the area of this trapezium here, okay, the perpendicular height for all these trapeziums is h. So the area of trapezium 1, we'll call it, is 1/2 h x0 plus x1. For trapezium 2, that's equal to 1/2 h x1 plus x2, so on. So you can see that x0, no, sorry, I'm putting x in here, that's wrong. It's supposed to be y, because it's at the point x, right, but the length of this line is y1, is y0, the length of this line is y1, the length of this line is y2, length of this is y3, and so on. So these are supposed to be y's, y0 plus y1, y1 plus y2. You see y0 appears once, yn will appear once, because they're only part of one trapezium. All the other yi's appear in two trapeziums, so that's why we get this multiplication by 2 here. And this is just the sum of all these trapeziums added up. So if we added up t1 plus t2 all the way up to tn, which is what we want, the half h comes out, we get these, and we get 2 of each of these, so we take them out there. Brilliant. So hopefully that makes sense. Yeah, we'll be back with some more numerical methods in the upcoming videos. Thank you for watching this, and I hope to see you in the next one. Have a great day.